Hello everybody, welcome back. So, okay, I filled in all the rock names, so now I'm just going to select all of it, and then obviously I'm going to group it once again so nothing gets moved out of position, and I'm going to simply copy, and I'm going to paste it, and then once again I'm going to rotate so it's horizontal. I'm going to use this as a guide so that I can make sure I'm right. You can see I'm not quite right there. There we go. No, I went too far. There, that's perfectly horizontal. And now I can just zoom in. So here I go. And then I'm just going to tweak this to get everything into the correct position. There. Okay. So we're all aligned. So now we know what layers of rock we have where. So what do we know is going on here? Well, we know that we have ST here. So we know this is a layer of ST from here to here. And we know that we have ST from here to here. Now that means that SC is the only layer of rock that doesn't appear anywhere else. So that means this must be the core of the fold. Okay, so how are we going to do this? Well, the SC must be dipping at the same angle as this, so 23 degrees. So this is dipping 23 degrees. This will also dip 23 degrees, and whereas this one here will be dipping at 20 degrees, because it's got to be consistent with these layers, hasn't it? Okay, so we will copy that, get it into position. Very, very thin layer there. Okay. And then we will do the same for this side. Okay, we're going to do this once again. Very, very thin layer there. And now we're going to zoom in. We're going to really get in close so we can get this sorted. Okay. So once again, here's SC. So now we are just going to make this the correct length. So the two pieces join together. Done. Okay. Stage 1 complete. So now we have to join ST to ST. So let's extend this. And this one goes to there, this one goes here. Remember, don't move the lines to fit, move them to the correct position. Okay, there. Okay, so then we have OJ, and here's OJ over here. So then we're going to extend this line, and then we're going to extend this line, and the two of them will meet here, like so, and so on. Okay, so now you can see you have the names, so you know which layer is which. You obviously have the dip angles. Now remember, even though these layers don't have dip information, they must be the same as these layers, because remember, this entire layer is folded as a package. Okay, this entire sequence is folding as a package. So all of these layers of rock will have the same dip. Same with these layers of rock over here, they'll all have the same dip. Okay, so everything must be consistent. Now, the one thing we do need to talk about is this fault right here. Okay, now it's a thrust fault, and most thrust faults will typically have a dip of around 30 degrees. So I'm just going to draw a line. I'm going to go to Format, Rotate, and then of course I'm just going to take it to 330 degrees. Remember, 360 minus 30. That's going to be approximately my fault. Remember, I'm just going to hold down the Alt key. Okay, going to put that there. Going to adjust the length of it with the Shift key. Alright, now I'm going to draw this as a thicker black line to show me that this is a fault. It's a bit too thick. There we go. Okay, and I'm going to assume that these layers of rock here will be consistent with the fault plane. So I'm just going to put another line here for these layers. Make those the correct length. Oh, bit didn't quite go to plan, did it? No, I'm going to have to use Alt for this one. And then obviously I would make that line the regular weight, which is going to be, what, 1. Okay. And so what I'm going to do over here is I'm going to start first of all by joining up these layers of the syncline. Then I'm going to repeat the same process over here for this other syncline here. Okay. Now as I'm doing this syncline over here and this syncline over here, I will naturally end up drawing the anticline as a byproduct of those two working out these two separate structures. The anticline just happens to get drawn through, for want of a better term, blind luck. So as you can see, it's a relatively simple process. All you have to do is you have to be willing to, number one, make sure when you take a screenshot you have the map and the section at the same scale. That's stage 1. And then you have to be able to draw a rectangle like this, which extends from point A to point A prime. And then you just simply have to fill in all the following information. The dots showing you when you're transitioning from one layer to another. The arrows and the angles showing you the dip and dip direction. And also the letter codes for each of the layers, so you can keep track of which layer is which. And eventually you can see, it's relatively obvious, you're going to end up with a syncline, anticline, syncline, anticline set. Okay, so that's it. I know it looks tough, but once you actually settle into it, follow the steps I've done, and once you actually start doing this, you are going to suddenly find that it's nowhere near as bad as you think it is. Okay? Alright, so have a go. You'll be surprised about just how well you do. Okay? You know, I know you can do it. Give it a try. Okay. So, next. So we've done that. So number 2. What geological structures are predominant in this part of Pennsylvania? Well, we know from our diagram that we have 2 structures which we were just talking about a second ago. They're types of fold. So I'm not going to give you any more information than that. So how can the pattern of a syncline on a geological map be distinguished from the pattern of an anticline? Well, if we go back to the map here, what do we see? Well, we know from our cross-section already this area is a syncline, isn't it? Look at the dip symbols. Okay. We know that this area here, from there to there, is an anticline. Look at the dip symbols. Okay. Look at the way they're facing relative to each other. Okay. Question 4. What type of tectonic stress, compressional, tensional, or shear, is indicated by the folding and faulting present in the map area? Well, we should probably be able to work this out quite easily. So if this is our layer of rock here, okay, if we are extending it through tension, what happens? We stretch the paper and nothing. Okay, well that didn't really work, did it? What about shear forces? Well, shear forces are a little bit more difficult to talk about, but essentially we'd be taking the 2 sides of the paper in opposite directions, and well, yeah, it's going to cause the area to deform a little bit, but in the grand scale of things, it's not actually going to do that much. However, as soon as we compress our layer of paper in this case, or a layer of rock, it's naturally going to want to buckle and fold. So think about it and write your answer here. And finally, list the 2 or 3 formations that appear most resistant to weathering and erosion. So you're thinking, okay, how do I know that? Well, typically the layers which will be most resistant to erosion will tend to form topographic highs. So if you look at your... So if we come down here and we look at this diagram here, okay, we can see that some layers are naturally forming topographic lows. These will often be layers which are more easily eroded. In contrast, areas that form topographic highs, like this little lump here, will tend to be more resistant. Okay, so something like OBE appears to be quite resistant, and it forms a little topographic high over here as well. Okay, you get the same thing over here with OJ, and you see OJ over here is also forming a little topographic high. So have a look at this diagram, look at the layers that you think may well be forming little topographic highs, because those are going to be the more resistant material. Okay, so that was part B. Now, because I'm not evil, I'm not going to make you do part C. Okay, so part C is not happening. Sorry guys, I'm just getting myself confused there. So part C is a no. All right. And finally, we're going to finish on part D. So what does part D involve? Well, part D involves this map at the back. There it is. All right. So it asks you several questions, so we're going to have to think about the map. Okay, so number one, which Paleozoic and Mesozoic geological systems are presented in the map area? Okay, a geological system is essentially the same as a geologic period. So you remember the periods of the geologic timescale: Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous. And then what's the next one? Paleogene, Neogene, and oh cripes, I've forgotten the last one. Holocene? No, wait, not Holocene, Quaternary. Oh cripes. Let's just hope no one I know is listening to that. So the question then becomes, which geologic systems, i.e. periods, are represented in the map area? So remember, Paleozoic and Mesozoic. So Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous. Those are your options, okay? So which ones are in the area? So if you want to know, go to the map, and it's quite nice because they've written it for you. Okay, you can't miss it. All right, so that's part one. So question two, which Paleozoic geological systems are not represented? So Paleozoic, Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian. All right, so which one of those, which one or ones of the Paleozoic geologic systems are not present? Remember, systems equals periods. Question 3. What is the nature of the contact between the Precambrian rocks and the base of the Deadwood Formation? All right, so let's find out what we're looking at here. So the Precambrian rocks are here. They're these two rocks here. So that's the orange stuff and the brown stuff. Okay. Now the Deadwood Formation is this orange layer coming down here. So the obvious question is, what is the type of contact we have there? Well, I'm going to tell you now, it's unconformable. And it's an unconformable contact where you have sedimentary rocks in contact with older, igneous, and metamorphic rocks. Okay, so you will have to work out what type of unconformity that is. Okay. Question 4. Let me get that straight. What is the nature of the contact between the Deadwood Formation and the Englewood limestone? How much time is missing? Okay, contact between the Deadwood Formation and the Englewood limestone. All right, where are we now? Let's find out. Well, we know the Deadwood Formation is. It's this orange line here. And the Englewood Limestone is this green line coming up here. This green bed coming up there. Okay. So obviously we can see we have our layers of rock. The Englewood Formation here in green. And we have the Deadwood Formation here in orange. Okay. So what can we say? Well, we know that the Deadwood Formation existed in the Cambrian. All right. So, when did the Cambrian start? When did the Cambrian finish? Well, this means that the Deadwood Formation could, in theory, have formed at the very, very, very last minute in the Cambrian. So, the starting point would be what is the date for the end of the Cambrian? Okay. It starts 541 million years ago, but when does it end? The Englewood Limestone, on the other hand, well, that's Carboniferous in age. That could have started forming right at the beginning of the Carboniferous. Okay, so what you need to know is how much time has been lost between the end of the Cambrian and the beginning of the Carboniferous. Okay, so to work that out, all you need to do is you need to go to a geologic timescale like this. Here's the end of the Cambrian. Here's the start of the Carboniferous down here. It's essentially a bit of simple subtraction. All right, so that one is not a particularly difficult question. Okay. So next is question 5. So what is the nature of the contact between the Sundance Formation and the Skull Creek Shale in the southern 1/3 of the map area? How does the relationship change northward along strike? Okay, so we need to find ourselves the Sundance Formation and the Skull Creek Shale. Okay, where's the Sundance Formation? Sundance Formation, there. Okay, is in blue. So it's coming up here. It's this rock formation coming up here. Okay. Skull Creek Formation is here in green. It's coming up there. Okay. So when you're in the lower third, so essentially from here to here, what's the contact between these two? Are they in direct contact with one another? Yes or no? Now, as we come up, are they still in direct contact with one another, or does something else get in the way? Well, you can probably see there's a black layer there. So this means the Sundance Formation and the Skull Creek Shale are now separated by another rock layer in between. So we can see there's a change in the contact between them as you progress from the south to the north. Okay. So the relationship changes essentially because in the south, well, you can tell me whether they're in direct contact, whether there's something in the way or what's going on. But as you move northwards, does something get in the way? Look at the map. So the question is as well, why? Why does that get in the way? Well, let's go back. So this thin black line here, or black layer should I say, is the Morrison Formation. So you have to ask yourself, why do all of these layers here, so the thickness is relatively consistent, they all maintain this north-south strike, don't they? So the question then becomes, why? Why does the Morrison Formation essentially appear, disappear, appear again, and then disappear altogether again? So you have to think to yourself, we've lost rock. So what process can mean you lose rock? All right. When you expose rock to what process, does it essentially does rock get destroyed? So that's what you have to think. And so once you worked out what process can destroy rock, well then it's relatively simple. You can say, right, well the Morrison Formation has clearly undergone this process. Hence the fact the rock has disappeared. Excuse me. It's rather late here. So we know we've lost rock, So we just have to come up with a process that can destroy it. And so we know what's left of the Morrison Formation appears here, it appears here, but here and here, the Morrison Formation has been completely destroyed. So you've got to work out what process is going to be doing the destroying. Question 6. So the tertiary White River group crops out on the eastern edge of the map. List the formations that are in contact with the base of the White River group. Alright, let's find ourselves the White River group. So the White River group is this rock here. Okay, this kind of creamy white. So it's all of this stuff here. So what layers of rock does this material touch? Okay, so give a list of all of the layers from here that it is in contact with. So you can see it's in contact with Kg. That's going to be the Greenhorn limestone. It's in contact with KBM. That's going to be the Morey shale. It's in contact over here with the KS. That's the Skull Creek shale, etc. So you can see it here, 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 and don't forget it's there as well. Okay, so what layers of rock is it in contact with? Give me a list. And it's going to be quite an extensive list. Question 7. What type of unconformity is represented by the contact of the White River group and the underlying formations? Alright, back to our map. So what do we have? Well, we can see that the White River group here has a horizontal dip because we've got the circle with the cross. Circle with the cross here, so horizontal bedding. It has a dip of 3 here and a dip of 5 here. The material is nearly horizontal. Okay, so it's more or less completely horizontal. Now the layers of rock underneath it, however, they're dipping at 19, 37, 38, 38, 45. So they are dipping at an angle. So what we have is we have a situation where we have tilted rocks underneath meeting horizontal rocks above. Okay, so below the unconformity we have rocks which have been tilted, and above the unconformity we have rocks which are horizontal, so they have horizontal bedding. So you have to go and work out what type of unconformity is that, and that's not a particularly challenging question. You should be able to work that one out pretty easily. So question 8. So steeply dipping Paleozoic and Mesozoic strata in the map area are part of the east dipping limb of the Black Hills Uplift, a structure associated with the Laramide Orogeny. We haven't covered the Laramide Orogeny yet, but we are familiar with the term orogeny, and we know orogeny essentially means mountain building event. So we know that the deformation or the tilting of the rocks that we're seeing here is related to the Laramide Orogeny, the Laramide mountain building event. Based upon the relationship seen in the map area, indicate the age of the Laramide Orogeny. Explain your reasoning. Okay. So the Laramide Orogeny is going to be an age range. Okay, it's not going to be a single number, because it's not like the Laramide Orogeny just happened in one day. It happened over millions and millions of years. So what we need to do is we need to use this map here, and we need to try and work out how we can show, when the Laramide Orogeny started and when the Laramide Orogeny finished. Okay, so how are we going to work that out? Well, let's have a think about what we can see. So to begin with, start having a think about these lower layers here and the fact that they are tilted. So we can see that everything from the Cambrian all the way up to the Cretaceous has been deformed. Okay, now that deformation will have occurred over a long period of time. So we can see that the Cretaceous has been deformed. So we know that deformation was definitely occurring essentially at some point after the Greenhorn limestone was deposited. So the Greenhorn limestone gets deposited as a horizontal sheet, then it gets deformed. Now we know by the time the White River group was deposited, the deformation had stopped. because the rocks are not deformed. They are nice horizontal layers. So we know that deformation must have been happening in the Cretaceous, but it must have stopped by the time we made it into the Tertiary. I should point out, by the way, the wording in this question is extremely poor, because the problem is the Cretaceous ends 66 million years ago, and the Tertiary starts 66 million years ago. So in theory, there's no time for this to happen. So what this would suggest is the deformation occurred in the very late Cretaceous and maybe continued into the very early Tertiary and then stopped. Okay, so this is a terribly worded question, and they should never have used the word Tertiary in this diagram. The word Tertiary hasn't actually been used for a while now. It's a very old term, so it's been replaced by Paleogene and Neogene now. So a bit bad that they actually used it. So anyway, what this question is actually asking you is, well, if you look at the map, you can see the Cretaceous rocks are deformed. So that means deformation of these Cretaceous rocks must have occurred in the late Cretaceous. But when we look at the Tertiary rocks, they are undeformed. Therefore, we know that deformation must have stopped probably sometime in the early Tertiary. And then finally we have question 9. How can the pattern of an angular unconformity be distinguished from that of a disconformity on a geological map? Okay, so prepare yourself for amazing art. Just trying to get this the right way. Okay, here we go. So an angular unconformity looks like this. We have tilted rocks below the unconformity, and we have horizontal rocks above the unconformity. Now this means on a geologic map, what you're going to get is you're going to get a meeting between layers of rock which are horizontal and layers of rock which are tilted. And you're going to see them meeting each other because there's going to be a contact between them. So if we go back to our map here, we can see we have an angular unconformity right here, because we have all of these layers of rock which are tilted. Okay, 35 degrees, 38 degrees, 37, 19. So we can see all of these layers of rock, 14, are tilted, and they're all tilted towards the the southeast. Now what's happening is over the top of them we have the White River group, which is, as we can see, horizontal. So this means you have a direct contact between the White River group and the rocks here, which are tilted. And so you have tilted rocks below, horizontal rocks above, angular unconformity. Now a disconformity, on the other hand, would present horizontally bedded rocks below the unconformity and horizontally bedded rocks below and horizontally bedded rocks above the unconformity, and the unconformity itself would be an undulating surface. Okay, so in the case of a disconformity, we would have something that actually looked like this. We would have groups of rocks all running parallel to each other, and the disconformity itself would not really show up on the map. You'd have to go to the outcrop and you would see the undulating contact between the layers, and that would tell you there was a disconformity there. So in angular unconformity, we have tilted layers of rock in contact with horizontal layers of rock, and this is a beautiful example right here. Excuse me, in terms of disconformity, we would have packages of rock all running parallel to each other, and you would have a disconformity running along the contact between them. So that would be the difference that you would look for in a geologic map. So by going through this part D, I hope you've kind of begun to gain a little bit of insight into how we can use a very simple geologic map like this to begin to work out what's happened to an area. Okay everyone, I think it's time to stop here because I've probably broken your will to live. So relax, have a walk around, get some tea, coffee, and then if you want to, if you have the energy to, go back, have a look at the cross section. I know it seems like it's a lot of work, but once you actually get going on it, you'll suddenly discover that it's actually super easy. There's a flow to them, and you'll work it out pretty fast. Okay everyone, so That's it for now. Take care.